the classical refactorings are not well suited for such feature-oriented development, since both the size of variance and the behavior of each variant must be perceived. The classical refactoring laws are too coarse-grained to apply in this context. One of the standard way to implement multiple variants is through clone and own, but the cost to maintain the clones and synchronize the change in replicas increase. Developers may benefit from migrating such variants into a software product line. In our work, we propose the catalog of variability of refactoring rules for colorful alloy. Then we show how to use these refactoring rules to migrate a set of legacy alloy clones into a colorful software product line. Finally, we show how to implement these rules and how to implement these individual rules and automatic strategy in the alloy analyzer. Next, I will present an overview of the colorful alloy through a simple example, designs of multiple variants of e-commerce platform. The design considers 3 optional features. The first one, allowing products to be classified into categories, and allowing categories to introduce hierarchical categories, and allowing products to have multiple categories. Like modeling with regular alloy, a colorful alloy model is defined by signatures with fields inside. In colorful alloy, certain elements can be annotated with positive or negative annotations, determine the presence or absence of variance. To ease the understanding, the analyzer introduced background colors for positive annotations and the colored straight-through line for negative ones. For example, we can declare a signature product. Inside product, we have a list of field declarations. The negative annotation and the colored straight-through line on field catalog means that it will only exist when feature 1 is not selected. Feature annotations can be nested, which means the conjunction of present conditions. So thus here, the signature category only exists when feature 1 is selected and feature 2 is not selected. Additional constructs are introduced by facts in alloy, like signature and fields. The entire facts or part of the expressions can be annotated with feature expressions. Once the model is designed, the user can instruct the analyzer to find a counterexample through a check command. The colorful alloy supports feature scopes on commands. For this particular check, the analyzer will verify a citation or cataloged for all variants that include feature 1 and feature 2. Or in our work, we propose a catalog of refactoring rules that covering all constructors, such as annotations, structural declarations, commands, citations, and involving all granularity level from the entire paragraphs to formulas and expressions. The refactoring law are present in the form of an equation between 2 templates under the context of a feature model. When the preconditions are met and either side of the template matches, the law can be applied. Here is an example law for remove redundant annotations. feature B can be removed or introduced when we have a feature model implies that A implies B. Feature A here, it represents a set of positive or negative annotations. Of course, it can be empty. I'll show this, I'll illustrate how to use this loss with a symbol example. In our e-commerce software product line, we know that feature 2 implies feature 1. So feature 1 is superfluent when feature 2 is present. So we can remove feature 1 by applying the law from left to right or added from right to left. Signatures with the same identifiers can be merged if it passes a specific annotation A on B, in which case the feature B can be removed from the signature and pushed down to the respective field declarations. So the two distinct signature catalog in our example, under feature 1, depending on whether feature 2 is selected or not, can be merged to one signature. The two distinct field declarations can be reflected with the next law, even though they have different bounding expressions. The final bounding expression is equal to the union of the two original bounding expressions. We also have laws for paragraphs and for commands and for expressions. To migrate these clones using the laws just explained, we first migrate to the plain Alloy models to a colorful Alloy model by annotating all paragraphs and the commands of each clone with a feature expression that exactly specify the variant. Then we combine all these clones to trivially correct but a verbose initial software product line. We also have a feature model that constrains variant to forbid variants that not exist in the model. Finally, we use a stepwise process to improve the software product line. For example, for the e-commerce example, the base model annotated with feature expression, not 1, not 2, not 3, because it does not specify any of the 3 features. The remaining variants are annotated accordingly. We also have a feature model constraint that forbidden the variants with feature 2 but not feature 1, and feature 3 but not feature 1. After this trivially merge, we can start the stepwise refactoring process. I'll illustrate the process with the signature product and the field category. We can merge the first 2 signatures. Then if we want to further merging, we need to remove the redundant feature 1. Keep merging, we can get the original we record the number of products, the lines before and after refactoring, the distinct loss used, and the refactoring steps. Take the e-commerce as an example. We have 5 clones in total and 102 lines before the refactoring, but only 31 lines after the refactoring. The migration achieved a reduction of around 72%. The process using 15 distinct refactoring laws and 101 steps to refactor but only 30 actions if we implement the automatic strategy. In average, we achieved around 52% line reduction. Our catalog of refactoring achieved a significant reduction in the model size compared to the plain alloy models. So we consider a simplified understanding of overruns. For the examples derived from the colorful alloy, the refactoring was sufficient to migrate the clones and obtain the original colorful model. In the future, we want to conduct a more extensive evaluation, and we also want to implement a SAT-based decision procedure for checking the preconditions of the refactoring loss. So that's our work. Thanks for listening.
Okay, thank you, Xiong. Thank you for the great presentation. We have time for questions. Let me see if there are any questions. Okay, there is no question in our chat, but I have some questions. What about the semantics of, you have transformations. I was wondering about the semantics that guarantees that these transformations are behavior preserving. So, of course, you use alloy, so that you have the alloy analyzer and the colorful alloy analyzer to check these transformations. But we have semantics of alloy transformations in PVS, a work done by Rohit, for instance. Have you ever thought about having these semantics of colorful alloy and these transformations in PVS or other proof assistant?
Sorry, I don't know about PVS.
Okay. So when you have,
maybe I can follow up on your question. Maybe it's what you were asking, but maybe is the question could be made like, how do we ensure that the refactorings are sound in the sense that they preserve behavior? And this would have to be dealt with according to a semantics. Maybe just adding a twist on your question, Marcio, but I'm not sure if that's what you were asking.
Yeah, that's the reason, how to ensure that the semantics is preserved with these transformations.
Until now, for this work, we do not consider about this semantic things. Maybe I'll do in the future work.
Okay, thank you. Another question, and it's related to the semantics. When you have, for instance, when you have provisos in some laws, for instance, you have a law with a proviso, for instance, law 5, you have a proviso. How can you reason that this proviso is sufficient? Is it strong? Is it weak? Is this sufficient to guarantee that the transformation preserves semantics? How to obtain these provisos?
Sorry.
In other situations, yeah?
I'm not really understand, but I'm sorry. about the
Okay, the question is about the proviso in law 5.
law 5.
Yeah, and we can have provisos in other laws. The question is this proviso weak? Is it strong? Is it sufficient for preserving for ensuring that the transformation preserves semantics? Also, this question is related to the semantics of the transformation, to the semantics of the law. Okay, so let's thank Sean. Would you like to have any considerations about these questions? Maybe you can we can have these questions discussed in the Slack channel. I think this we can proceed in this way and have these questions in the Slack channel. Okay. We can discuss this in the Slack. So thank you, Sean, for your presentation. Thank you for your talk. We can go ahead with the other presentation. That's going to be, let's see, it's Tayonara.
She had connection issues. I'm trying to contact her.
Okay. Leopoldo, do you have a video also of this presentation?
Yes, we do. We have a backup video for.
Yeah, not me. No, I think
okay,
they have.
Okay. Thank you, Gustavo.
Leopoldo, so shall we play the video instead, or do you think that we may switch the order? So, what do you think, Leopoldo?
Whatever you think, it doesn't disrupt the order. I mean, she had connection issues, so she went to a relative's house, and she's just getting there and trying to connect. From what I heard a couple minutes ago.
So
either we wait or I go ahead and present. There's no problem from my end.
If Marcio agrees, I think that we may switch the order to give her a second chance. What do you think?
Yes, I think that's right. Gustavo, do you have an announcement?
Yes, I have a small announcement just to remind you that we kindly ask you to vote on your favorite presentations at ETMF and SBMF, because as soon as this session closes, I will close as well the two forms to announce the winners in the closing session. So please vote if you hadn't.
Okay, thank you. So Leopoldo,
I'm sharing my screen and just a sec. I think you all can see now.
Yes.
Just put my video so you can see my face, because that's very important to understand. No, that's the idea, right? Okay, should I go? All right, good afternoon, everyone. My name is Leopoldo. I'm an assistant professor at Federal University of Pernambuco. This is a joint work with Rohit, who was a keynote speaker last Wednesday at SBMF, and he's at the Federal University of Campina Grande, and Paulo Borba, who's also at the Federal University of Pernambuco. This work deals with the evolution of product line, and we try to do this safely by using what's called configuration knowledge laws. So we'll go unpack this title bit by bit by trying to explain each term, the meaning of each term. So first, let's get an overall idea of product lines. This work has a relationship with both the first paper that was presented and the following. So the idea of product lines is mostly a set of software products that are somewhat related. So they are distinct from each other, but they share similar characteristics. And those products are built out of reusable assets. So by assets, you can have code, image files, requirements, documents, architecture. So any kind of asset that can be combined to produce a product. So in our case, we illustrate this by having these 3 games, 3 versions of the same game. And in one version, you have the clouds moving, and another version, you have the clouds stale and static. And in another version, you have no clouds. So this was an example that dealt with differences in terms of memory for older cell phones some years ago. So to deal with this so-called variability, you usually do not focus only on code, but you also have to rely on other artifacts. So for instance, you typically describe in a high level of abstraction the features. So this variability usually is described in terms of features by means of these feature models which model the variability of a product line. So you see, for instance, that clouds is a rectangle with a white filled circle on the top. So this denotes that this is an optional feature. You can either have clouds or not. And below clouds, you have the white filled arc. And this denotes the alternative feature. So you either have clouds static or moving. These are mutually exclusive options. So you have assets in a concrete implementation of features, and you will need something to bridge the gap between these high-level abstractions, features, and their implementation. So this is the role of the configuration knowledge. It acts as this bridge, as this middle way between features and assets. So this knowledge could be implicit. So we just seen a presentation about colorful alloy, and it drinks in the fountain of feature-oriented programming, where this is typically implicit in terms of the structure of your code. It might also be scattered, as in C preprocessing directives, as you see in highly configurable systems. Or you can have it modularized in such a model like the one I'm presenting to you. So this model basically relates feature expressions, which are propositional logic expression over feature names, to assets. So it's a very simple model, this one. We can have other kinds of relationships. Instead of assets, we could have general transformations, but to keep it simple, we're showing here association with feature expressions to assets. So if you select either on demand or startup, you see that on the second row, we have the common image load Java class file present in your software product. So this model, together with a particular feature selection, drives product generation. So these 3 models, these 3 elements, feature models, configuration knowledge, and assets, they constitute a product line, as we will see formally in a bit. And by means of selecting features, you evaluate this model and produce a set of assets. And this is essential for this automatic generation of software products in a product line. But what if you have problems in this model? you can have a number of different kinds of problems. You could have missing entries, so missing assets, and this would lead to probably compilation problems or problems of related to well-formedness. But even if you consider a well-formed model that does not refer to inexistent features or something like that, you could still have some problems. So focus now on this particular row where we have on-demand or startup associated with this class common image load. You see in the feature model that both on-demand and startup are different image loading policies, but they're both image loading policies. So you have some common code between those two. So here we express that by saying that if you select either of these, you include the common image load class file. But what happens when you add a new feature? So now you have, besides everything being loaded on demand or on startup, you have a hybrid version. So now the same model that you had, if you don't change this feature expression, now you have probably potentially a problem because this common image load class would not be associated with the hybrid feature if you don't take that into account. So our goal in this work is pretty much propose a number of refactorings that we call laws because they are equivalence relationships between the models, focusing on improving this internal structure of the model while preserving its semantics. So as the product line evolves, you might have some quality deterioration of this model. So we need to take that into account to avoid problems of maintainability. So let's now try to define, this is a formal method symposium, so let's try to formally define our concepts to present the general idea of the work. As I mentioned, a product line for us, for our purpose, is a triple feature model, assets, and configuration knowledge. So I already showed you the F and the K, but the A is what we call the asset mapping. So this is a mapping from names to actual artifacts. You can see that, for instance, we can handle conflicting assets in this way. We have two classes named main. In a regular software project, if you had these two classes in a particular folder within the same package, you would have some conflict in your compiler, in your IDE. The idea here is that we can handle this by means of this indirection, by associating names with artifacts. And this, as mentioned, these three elements produce well-formed products, and this well-formedness notion is associated, for instance, could be associated, for instance, as a product is compiling or not, but this is generally defined in a general theory that you can provide your well-formedness notion. So the main idea of product line refinement, which formalizes safe evolution, is this idea of lifting the behavior from products to product lines. So the definition of a product line refinement is a change to a product line where you preserve the behavior of all of your products. You see in the left that you have 4 products. They are represented as stars just to abstract away the details. And you have in the right side another product line where you also have some products, but now as a square, just to mention that you could have changed something in the structure of these products, but you see that there is some correspondence between the 4 products that you had before. You have a corresponding product on the right. So this is formalized according to this definition. You see that whenever any configuration of your feature model, so this is the meaning of the brackets, the double brackets as in F, there exists some configuration in the new feature model that refines the existing product. So you could actually have more products, but you need to have at least the same the products that you had before should be their behavior should be preserved. So Based on that, we introduced a notion of equivalence for feature models. So the idea is quite straightforward. For any configuration of the feature model, evaluating this configuration knowledge model before and after will yield the same set of assets, right? So this is a relation that's indexed by the feature model. For instance, let's see an example based on what we've just discussed. So you see here below the feature model, two different models, configuration knowledge models, that are equivalent, because having on-demand or startup is equivalent to having image load policy as a feature expression, but this is only true when you have this particular feature model. These are not propositionally equivalent, because these names do not mean anything other than the relationship established by the feature model. On the other hand, you see that if we introduce hybrid feature model, these cease to be equivalent. So these are not equivalent configuration knowledge models. And why do we care about the equivalence of configuration knowledge models? Because we also have this result of compositionality. Since a product line is composed of three elements, the feature model, the asset mapping, and the configuration knowledge model, we have this compositionality result stating that if you evolve independently the configuration knowledge model and you result in an equivalent model, then you have the refinement of the product line, thus the safe evolution of the product line. So based on that, we proposed a number of laws and that ensure that you change the model resulting in an equivalent model. So for instance, I will go briefly through all the laws. So for instance, we can, as we've just seen in the example of on-demand and startup, we can replace one feature expression by another whenever they are equivalent. And in this case, they could be equivalent by the feature model, as we state in the condition. And in a particular special case, they could be propositionally equivalent. You could have A or A. I mean, who knows why you would write something like that, but it could be the case, right? So you can just replace that by A. So this would be useful, for instance, to make a complex expression a bit more simpler. You could focus on the maintainability, so replacing a large OR expression by their parent, if that's possible, right? So this is a particular law that you can apply, and you see that there is an equals sign, so you can go from left to right and from right to left. This is true for all the laws that I will present in what follows. So our second law is that whenever you have different entries in this configuration knowledge, so you see two rows in the left that have potentially different feature expressions, they for sure have different assets. So you have N and N prime, but these are different expressions, but they are equivalent. So you can merge choosing one of those expressions and have all assets in the same entry and associated with a single feature expression. They could be the same expression with different assets, but that's the idea, right? In a similar line of reasoning, we also can have here in the previous law, we focused on things that are equivalent on the left-hand side of the model. Now we focus to the right-hand side of the model, and we see that you have different expressions, but you have the same asset on the right. So you could just join those expressions with an OR and resulting in a single entry associated with this asset. So this could be a way of reducing the size of this model, but in the other hand, you could introduce a more difficult feature expression for you to read. So that's something that should be taken into account while performing some of those changes. One thing that can happen is that some relationships might change, or you could actually introduce some problem in your feature expression, and you could have what's called a dead feature expression. So here, the idea is that no configuration of this feature model, no feature selection would ever activate this expression, this presence condition. So it's always evaluated to false. So it's pretty much the rationale here is this entry does not contribute in any way with the model, so you can remove it. Of course, you could also, it can also mean that you can always add dead feature expressions to the configuration knowledge model, but again, there's not much point, there's not a very useful way of evolving your model, but it's possible, and we also prove the both sides, both directions of the change. And finally, we have this particular kind of model where we just associate feature expression with assets, so the order doesn't matter that much in this kind of model. So we can always switch the order, and this could be useful for preparing a transformation, preparing the model for another transformation, or for applying another law. In some other kinds of model where you have the notion of presence conditions associated with transformations, this could not be the case where the order doesn't matter. So we have these laws, but okay, how do we ensure that these are sound and according to the equivalence notion we've just mentioned? We prove these laws using the PVS, proof of system. So we have an encoding of the feature model, we have an encoding of this particular configuration knowledge model, and we pretty much translate those syntactic relationships. So we have here two models, one in the left, another in the right. The feature expression in the left-hand model is X, the feature expression is X prime. So these are all relationships that we can easily see by the syntax of those models as represented in those templates. But we also have semantic conditions. So these are those conditions that show up below the transformation. So we encode those relationships also as predicates. And for each law, we have a theorem in PVS that states that for any feature model and any configuration knowledge in which those syntactic relationships and those semantic conditions hold, we prove that those are equivalent models, right? So this is performed for each of the laws that we have proposed. And also we already had the compositionality result that states that if you have an equivalent configuration knowledge model, you have refinement of the product line. So this entails product line refinement and safe evolution of the whole product line. So the idea here was to ensure the formal part and the soundness of those laws. But we have also studied and evaluated those laws under a case study. So we have analyzed a product line of tools that automatically generate functional tests from use case documents written in natural language. So this is a tool called Target. It has been used by a mobile phone company to generate tests for its devices. It has 6 releases, and we have looked into the particularly into the changes from the 4th release towards the 6th. So this is a 1-year time span that we're seeing here from the release 4.0 until release 6.0. And in the latest release, it has 32,000 lines of code. So we manually analyze the transformation of the last 3 version releases. So a particular difference here is that these were coarse-grained commits mostly. So it's different from what we are used now to have with Git and practice of always committing. And so we have found, but even given this situation, we also have found instances and examples of applying the laws. So for instance, we have a particular commit, and I'm abstracting away for simplicity and also for non-disclosure agreement reasons, abstracting away the feature model, the entire feature model. But here we have the situation where we had a feature expression that was replaced by the parent. So this is an example, for instance, of the simplified feature expression. We have found another instances of those laws, such as merge items with equivalent feature expression. So we have a bunch of different entries were associated with the same feature expression. So this was merged into a single entry where we have the feature expression and all the assets associated with it in the right. So we also found two more cases where we could justify the change using the laws, and this gave us this preliminary evidence that these laws would be interesting to have those mechanized. So in a master's student that was advised by Paulo, he implemented a tool for checking refactoring of product lines and refinement of product lines. So he implemented some of those checks and generated tool support for checking these kinds of changes. So in a nutshell, I've presented that product lines usually have different models to organize their vulnerability. These models can have problems. We have formalized the notion of equivalence for configuration knowledge models, and we also linked that with the product line refinement notion. Based on this equivalence notion, we proposed a number of laws that were all proven sound with respect to this equivalence notion, and we have also found evidence of their use in a particular product line that has been developed for an industrial partner. So with that, I conclude my talk, and I'm glad to take some questions.
Thank you, Leopoldo, for the great talk. We have time for questions. Let me see the question and answer. Oh, sorry, the chat. We have no question in the chat, nor in the Slack channel. But I have some questions. You have now a relaxed notion of equivalence. This notion now is weaker than the previous one. In the previous one, you have a refinement as a pre-order. Now you have relaxed this to have these equalities. Do you think the first notion, the previous notion, was not so practical in terms of product lines as you have now? So that you can express few product lines than you can express now?
There are two different notions that we are dealing, right? So this, the equivalence notion that I'm talking about here is particularly for configuration knowledge models. So this is just one part of the product line.
Yeah.
The product line refinement notion, it's the same as we had before. So
Okay.
this is the pre-order, and you could have
okay.
You could have the same properties that we had before. We just connected the idea of equivalent models result in product line refinement. The thing is that what we had before is that we had a stronger notion of equivalence for configuration knowledge models, where you would have the equality not constrained by the feature model. So it was stronger in the sense that it should hold for any configuration, regardless of the feature model. So that would be more, that was stronger than saying that, okay, for a particular model, any configuration from this model results in equivalent. So this this is more like a bounded equivalence notion by the feature model.
Okay, thank you. There's a question by Ana Maria. The target example was a bit quick. Can you explain it again?
Sure. Sorry about that. I was looking at the time and was worried, so I had to rush a bit. So the idea here is that we have looked into the artifacts of each commit of this product line that we had access. And in some of those commits, the developers have performed changes that were compatible with the kinds of changes that we propose on those laws. So that's the rationale for what we have investigated. So we have looked at so each circle is, you could see that as a commit, and so for each circle you have the before and the changes that have been applied. So in some of those commits we see changes where we have inspected the configuration knowledge model, and we see that, oh, here there was a change that it's an instance of the simplified feature expression. It's an instance of the sorry, it was not changing the slide. So we have seen in the commit that, oh, developers have replaced this feature expression in the left that was associated with two different output formats by the right-hand side that focused on the parent. So yes, it had been done manually before. So this is a retrospective analysis. We have looked at what developers have done, and we have seen that, oh, they do. So this is basically that's an evaluation of the expressiveness of those laws. So they are expressive to justify changes that have been performed by developers. But of course, they could do more kinds of these changes if they had access to some tool support at hand while performing the changes. Thanks.
Thank you, Leopoldo. You have time for one more question. So, thank you, Leopoldo, for the great talk. And we are going to, let's see if Tayonara.
I'm checking here. She said that
here.
she asked to join and everything froze there.
Yes, I think this was the second time she asked to join the meeting.
Yeah, I don't know what's going on. I mean, sadly, her connection is very bad.
Yeah.
Yes, I think that she's having some kind of internet connection problems because she was online just a minute, but she's off now. So
yeah, maybe we just have the video to honor her effort as well. And I'm here to take questions, so
Okay.
Let me just check with her.
Yes, I'm with her video here. I will try to present it.
Okay. She would just give it another try. So let's just see if she said that Zoom was freezing. So sorry about that, but let's see. Just if not, then we use the video.
Let me just check if
please,
was needed.
please.
The video is playing, correct?
Yeah, just to see the audio. We cannot hear the audio.
Oh, let me check something. Can you read the audio?
No.
No. Don't you have some setups now? Yes, now it works. Okay, so
can you hear?
Yes.
Yes. Okay, so
we're waiting for some minutes for her, or
yes, but she still wasn't able to enter, so I think we should just go on. Sorry.
Yes, I think it's time so that you can go ahead with the video.
Okay, I will put the video.
So this is the
okay, my name is Sayonara.
okay. This is the last paper in this SBMF edition. Work by Sayonara, Leopoldo, and Vander, and Thiago. So let's go ahead with the video, please.
Okay, my name is Sayonara. I'm a student at Federal University of Pernambuco. Actually, I just successfully defended my master's dissertation that I had submitted. And this paper was written together with Professor Leopoldo, Mari Basel, and Professor Vander and Thiago. So I'm going to start with some motivation of work, start with the proof system. And it is a fact that to write and check proof is not easy task, especially because some proof are so specialized that very few people can understand them. And some people are so long that very few people have time to read it. So it's a side way to manipulate by computer. In this context, we have the proof system. They can take as input in formalized proof, any check it is valid. In such a system, it is possible to write specification, defining proof properties with the help of a user, of course, but to use a proof system, we need the user interface where with terms by intra-sequence of commands following tactics. Also, internally, there's the proofing engine, which is responsible for building the proof terms for the inputs of the user proof system histories. These proof terms are not invisible to the user, but they are checked throughout the construction of the proof. And one of the most proof system, and the one we choose to use as scope, the main motivation for these tools are the constant improvements that for providers, the team of the Cox developers is always brings improvement to these aspects of the expressiveness and usability. Also, Coffee has a large user community, and there are several channels to reach this community in development team. Second, the Flow and GitHub, for instance, have a strong presence of Coffee users, and also the community has built tools around the Coffee system, and they bring a lot of documentation. Besides that, there are interesting features of Coffee, but the type class that we use in our work, the possibility to swap code for language like Haskell, for automatations, all of which motivates the choice of code. The motivation is also related to solve product lines. This concept brings several advantages, such as productive and quality improvements, apart from the capacity to customize a system based on customer needs. But there are several challenges in product line development field because due to requirement changes, they naturally evolve and tend to become complex to manage. So developers face the challenge in evolution scenarios. And one might need to check if a product had the behavior preserved in this situation. And product line defining features support that by requiring behavior preservation for all existing products. And this theory that we also decided to formalize in code. Well, also because the theories have been coded in proof using PBS, another proof system. So the purpose of the study is one, to put the theory to a system used by a wide user community, and two, to provide a case study on this process. And this enables to reflect and investigate the similarities and differences between the two proof systems in terms of the specification and proof papers, which might be useful for the research community to better understand the strengths and the weakness of each tool. For our purposes, product line are formally represented as a triple, a feature model that contains features and dependence among them, an ASCII map that contains set of ASCIIs and ASCII names, a configuration knowledge that allows features to be related to ASCIIs. Now we presented the main result for our work, and in order to avoid the repetition, we want to show the formalization in code in parallel with the original specification when they are different. Otherwise, we only show the code. Right, the present formalization can be organized into the following group. We have the concrete theories of feature models, STMAP, and configuration knowledge. And also we have the specification of the general SPL refined theories. Type class was used to associate between the theories, and templates that support developers and evolution scenarios were also formalized in code. This is a file-by-file comparison where the copy file are compared to the two PVS files, the .pvs, which is a specification file, and the .prf, which is a proof files. Okay, recursive functions are introduced with the keyword fixed point. We have the names function as our first recursive definitions, and it returns the set of names, the features names, using a given formula. In PVS, to specify recursive definitions, we need to prove TCCs to guarantee that the function terminates. And this is done by the major keyword that we receive a well-coded order relations to show that the recursive function is total. But Coq employs a conservative syntactic criteria to check the termination of all recursive definitions, allow recursive calls only in static subterms of the original primary argument. In SPL, the equivalence and refining properties justify safe and stepwise evolutions of features models. For that, we have the semantic of FEMs that are given by the set of all models configurations. In Kotlin, following operational specification, we use the JCOM functions, which generate the point set of the FM's features, and then we use the features functions, which takes the FM's reference into account. And meanwhile, PVS allows the definitions of sets using subsets, which allows the simplified declaration of these functions. We also establish compositional properties, which are the necessary conditions for guaranteeing the safe evolution of set product line when individually involved on its members. And the full compositional theories enable reason when all three of them involved. And it basically states that if we change the FEM in CK, resulting in an equivalency model, and then AM is refinement. The formalization PVS is similar to that of the Coq, except for the use of the where recommended to define a result SPL. About SPL refinement, it doesn't rely on a particular concrete engine of a feature model or configuration knowledge in SMAP, but it enables to establish refinement templates. In PVS, we do this with the theory interpretation mechanism, where we use the import recommended to provide the parameters for the unexpected types and functions. So this generation proves obligation that we must prove to show that such associations is constant. On the other hand, in Coq, we use a type class. We establish the SPL class with interface declarations and required properties, which are defined as axioms and theorems. And as we import the functions from the other type class, we need to render the constraints. And these constraints are satisfied by this parameter here. We use the program stance keyword to define a concrete stance, and we must prove that each parameter satisfies the previously defined properties. And Coq generates obligation for the remind fields, which we can prove using the next obligation keyword. And then we are able to prove thousands of the refined templates. These templates work as a guide for developers in evolution scenarios. They do not need to understand the theory for these scenarios. They just need to understand the templates. And these templates show the representation of the FEMs, AMs, and CKs. The FEM representation only shows the features involved or affected by the evolution. AM is represented by two square brackets with meta variables to indicate the name of the entities and the entities. And finally, we have the CK composed of the two columns. In the first columns, that are the meta variables for the expression of the features, and the second, the meta variables for the names of the entities. In here, the template of the replace feature expression show that if you the developer wants to substitute a feature expression, all product configuration of the F should lead to an equivalent evaluation for the original and resulting feature expression. The developer is also referred to using a new feature expression that reference F names. Then we specify the templates functions that express the similarities and difference between the original and result SPL. First, we have the syntax functions, which represent the syntax relationship between the initial and evolving product line. For this picture, syntactically, we have the original CK corresponding to the owner of a given item 1 with items, which are the other items that do not change. And we also have the result CK corresponding to the owner of item 2 with items, and the set of the S's of original item and resulting items is the same. Another function is conditions, which represent the transformation preconditions so that change is safe. In this case, the constraint is that all configuration of the F leading to an equivalence evaluation for the feature expression of both the item 1 and item 2. We also specify that the features expressions in item 2 as well typed with respect to F. About the truth, although we are reporting an existing PVS specification, the proof methods often differ between the two systems. For example, the lemma. In code, we prove the lemma by induction, and we use a sequence of tactics to prove both the basic case and the inductive case. The PVS proof, on the other hand, is simpler. The foundation of the PVS logic is also based on set theories, which influence in this simplicity. And here, it's clearly explain the association rules were used to complete the proof. And to compare proof commands of both systems, we have clustered the tactics and proof rules in 5 categories, according to the effect on the goals. The first of them is proving simple goals. So this command proves simple goals. Secondly, we have the transforming goals or hypotheses. This command allows you to make progress toward solving a goal. The next category is breaking apart goals for hypotheses. The following tactics and rules breaking apart goals into several simple sub-goals. And category 4 is managing the local frontage. In this case, there is no direct progressing in the proof, but this command is bringing improvements that might facilitate such progress. And then finally, there is the category of automatic commands. So the table presents the number for such categories in our proofs. First, we note that the number of tactics in copy is 47.7% higher than that of PVS. Besides that, the PVS specification has taken more advantage of automatic commands in the system. The results are approved using the grind rule, and in other 6 proofs, this command the result of all the sub-goals generated by the commands from the category 3. A great number of commands that make changes to goals can be explained by the great numbers of branches generated from the category 3. For instance, induction was used 15 times in Coffee and only 5 in PVS. Also, for sub-goal generation, we mark which one with bullets in Coffee increase the number of commands in the category 4. And to provide some external variable analysis, we also mine about 2,000 code repositories from GitHub. We have also categorized the tactics from these projects. This figure is comparing the distributions of commands among the categories for both our specification and the data from the GitHub projects. The percentage of the transforming goals or hypotheses is similar, but the proof simple goals appear more often among GitHub projects. In addition, automated commands are included for these projects. An interesting fact is related to copy hint command. This command serves the proving properties into a kind of local database. And in project where the hint command was found, 16.48% of the tests are automated, and 5.38 in projects that have not made such use. This suggests that we could have simplified our proofs using this command. We put some discussion in lesson learning in our work, and first, it's important to highlight that participants of this research had a much stronger proof experience in PVS than Coffee, so this certainly has an impact in our results. But in general, both specifications are similar for most encoders. Here, the biggest difference is in the number of the functions in recursive functions, nor use a dependent type in Coq meant that we use a few more definitions to express what had been defined in PVS. In conclusion, we put the existing SPL refinement theory recognizing in PVS to Coq. We also compared Coq and PVS using a developed specification. A comparison of proofs was also made, and we concluded that Coq formalism and the language are standard expressed to deal with and represent the different types of definitions found in PVS specification. But PVS provides a way to simplify most of the formalization presented as well as the proof rules that reduce the proof effort by the user. But Coq brings features such as hint, statistical command, dependent typing, and advanced notations in which users of this tool can overcome this difference.
So maybe Leopoldo can answer some of the questions. We can discuss a bit this work.
Sure.
Yes, we have no questions at this moment on the chat. So we have a similarity between the definitions in Coq and PVS. The main difference is related to the implementation of set. The definitions related to set in PVS and Coq. In Coq, you have set as lists, implemented as a list. Do you think if you had a toolkit, the differences would be, the number of differences would be smaller than we have now? A toolkit for dealing with sets.
Oh, okay. Yes, probably yes. But you have also, we could also have, there is this ensemble library from Coq, but this does not provide the means for us to compute. So sometimes we do need to check two elements, to grab one element from a set and to manipulate that. So had we had a similar mechanism, sure, I think these would be much more similar specifications in both theorem proofs. But on the other hand, as Tayonara mentioned, we had far more experience in PVS. So even doing this Coq, as I mentioned in the morning on my tutorial, we have a Coq specification with a high accent of PVS, highly influenced by the PVS style of specification. That was also, I mean, a decision during her master's, because so it was the kind of the easiest, in the sense, not easiest because some Coq expert would say, oh, it could be done this, you could have done this more easily in another way, but it was maybe easiest to make sure that we were mapping from one to the other and making sure that we were doing exactly the same thing.
Do you think you could benefit from QuickCheck, for instance, to express some relations for refinement and things like that? This is a benefit of using Coq, having QuickCheck for testing, for dealing with tests based on properties. So maybe you can consider this in a future work.
Yeah, that would be interesting if we consider starting with the refinement definition and comparing two particular instances of product lines. So that's why what I'm thinking about now. I had not thought about it before, but we have so this refinement notion. It can be explored. Usually, the most of the work I've done was exploring it in the sense of providing changes, as I've just presented in the previous talk and previous works as well. So we have this template. So here, change it like this and that, and we make sure that this is a refinement because we have proved that this is according to refinement. But we could also have this idea that, okay, just change, we will press a button and we have this tool set that will check whether this was a refinement or not. We have explored extending, for instance, safe refactor that Rohit presented on Wednesday to the field of product lines. But again, but this is mostly testing, generating random tests and applying that, and there's a scalability problem. Quick check. I would have to think more like we'll have to think about the encoding of the concrete product lines for comparison and generating tests, but it could be a side effect of having it in Coq.
Yes. Okay. Thank you, Leopoldo. We have time for other questions. Let me see. We have no questions in the chat. There is a question by Ana Maria. And do you expect the other way around would be also simple, or would it be more difficult to make a Coq spec fit PVS?
That's a good one. I would say that had we done the same way and with the same background that we have in PVS, but no background, so in Coq, but no background in PVS, I think we would probably face some similarities because we would be influenced by the characteristics of the system, but in particular, considering the way that we express this formalization, regardless of theorem provers, right? So in math, it's simpler to do it in PVS from my experience so far. So I haven't said that we would face some difficulties, but I think that it's at least so far, I think it's more straightforward. But this particular theory, right? I wouldn't say that any theory is more straightforward to do it in PVS than Coq. There are some things to do with inductive data types, and pattern matching is way more simpler in Coq than in PVS, and even more elegant, I would say. But in this particular case, I would say that it would be simpler. But I guess, right? That's
okay. So let's conclude our last technical session. Thank you for being here. Let me see. There is it's a message by Gustavo on the Slack channel, calling us to reminding us that this is the last chance to vote, as the forms are going to be closed soon. We have 10 minutes.
I thought the election was on Sunday.
10 minutes remaining. Yeah, 10 minutes remaining for our answers in the form. So thank you very much. The closing session, Gustavo, it's going to happen
at 4 p.m.
At 4.
Brazilian
okay.
time.
Okay.
And
so,
during the closing session, we are going to announce the winners of all awards.
Okay. So thank you. We have some time, and we can gather again at the closing session. Thank you. Bye.